Okay, in this video, I want to just give an overview, kind of a refresher of some of the most common basic statistical tests. I won't go into a ton of detail or dive into any calculations, but we'll kind of feel out what test you're most likely to use in a lot of common, simple situations. So I'll start with just a real high-level overview of the main tests that you might learn in, say, an introductory stats course in social sciences. Let's say, for example, that you want to compare people in a good mood to people in a bad mood to see who offers the most money to a charity cause. Or maybe you want to compare men to women to see which group pays more for car insurance. Or you want to compare those who got cognitive behavioral therapy to those who got medication for anxiety. In all those cases, you're comparing two groups of scores on some numerical variable, in which case the typical test is a t-test, and you'll likely calculate a t-value when you run the stats, or at least the program that does the test for you will spit out a t-value, and from that, it can also determine the p-value. That's what tells you if it's statistically significant. Now we'll come back in a minute and talk about those different types of t-tests that there are. I'll cover those in kind of some future videos, but in general it's easiest to think of it as your way of comparing two groups on some number. But what about when you have three or more groups you want to compare? When you're comparing 3+ groups on a numerical variable, the most standard test is an ANOVA, which is short for analysis of variance. It spits out an F value, or the stats program spits out an F value, and from that you can find the P value to see if the test is statistically significant, to see if you reject the null hypothesis. And again, I'll get into the details of that in an upcoming video, but just to preview ahead, if your ANOVA comes out significant, what that tells you is that at least one of those groups differs from at least one of those other groups, but it doesn't tell you which ones. So you can basically, you can figure out there's some difference in there, but you will have to do additional follow-up tests, what we call post hoc tests, to figure out which group or groups are higher or lower than the other groups. So we'll talk about those post hoc tests in a future video about ANOVA. Meanwhile, though, in both of these tests, you're comparing groups on some number variable, right? But sometimes you want to know if there's a relationship between groups and some categorical variable. Like basically sometimes your study might just have two categorical variables. Like let's say race and neighborhood. And you want to know if there's a pattern where some categories in the first variable are more likely to occur among some categories in the second variable, or whether those two categorical variables are unrelated in some way. So for situations where you're comparing like two or more groups, so some categorical variable, on a different categorical variable, for that, you would use what's called a chi-squared test. The statistic you calculate, or what you get from your stats program, it looks a little like an x squared, but that's the Greek letter chi, hence the name chi-squared test. So this is basically when you've got two variables that are both categorical. Now, before we move on, just a reminder. None of this stuff tells you whether the study design was experimental or non-experimental. Like, we don't know from this alone whether we're dealing with causation evidence or just correlational evidence. That stuff depends on whether you did an experiment, whether an independent variable was manipulated. So if you, say, randomly assigned people to be in two groups, and then you're comparing those groups on some numerical DV using a t-test, then that's an experiment. And you could talk about the IV causing the DV. But if you just measured the group variable, like if it's pre-existing groups, like men versus women, or self-identified cat people versus dog people, then a t-test would only tell you that those variables are associated, but it couldn't make a causation claim. So just keep that in mind. The statistic that we use has nothing to do with the whole correlation versus causation question. That has to do with more the design of your study. Okay. But getting back to the kind of common basic stats tests, there is another one I want to cover. But I'm going to try and be really specific with the name here. If you're measuring two numerical variables, like let's say height and weight, or like depression and income, both measured as a number, then you'll usually do a stats test that involves calculating a Pearson's correlation coefficient, which is the R statistic you've probably seen a lot before. When we say an R value goes from -1 to +1, meaning like a strong negative correlation to a strong positive correlation, we are talking about a Pearson correlation coefficient, an R value. But that tells you about the effect size of a correlation without doing a significance test yet to see if the correlation is real. So when you actually run a correlation stats test, an inferential test on two numerical variables to see if they're related, behind the scenes, your stats program is going to output a t-value actually, and you can use that to determine the p-value, where you figure out if the correlation you're seeing is statistically significant. In other words, whether the R value you found is telling you about a real correlation, in order to answer that, we have to do an inferential statistical test, which will crank out, it'll do kind of a t-value behind the scenes, but that'll allow you to find a p-value that you can compare and be like, oh, is my p-value low enough? Is it below 0.05? If so, I would reject the null. I would say the correlation test is significant, and then you can interpret the R value as how big the effect is, how big the correlation is, now that you're clear from this test that it's a real correlation. So just to clarify, there are two sources of potential confusion here that I want to try and keep clear. The first is that the R value in a correlation test, it is not how you figure out whether it's statistically significant. The R value doesn't tell that. The R value is our effect size. But we still need to do an inferential stats test to get a p-value and decide whether to reject the null or not. The other potential confusion is that the R value we're talking about here is calculating a correlation coefficient, a specific number of how related two numerical variables are. But we do also use the term correlation more generally when we're just talking about correlational studies. And in those cases, we can be talking about categorical variables and groups and stuff like that, not just numerical variables. So if I say that a study was a correlational study, I'm just saying it's not experimental, so we don't know about causation. We only know about association, relationship between the variables, whatever those variables are, whether numerical or categorical. Okay? But if I talk specifically about a Pearson correlation coefficient, if I talk about that R value, or if I'm discussing a correlation test, then we're specifically getting down into something with two numerical variables. Number variables have to be measured as numbers. All right, and then finally, just one last thing I'll mention here is that sometimes when you're just measuring a couple numerical variables and you're going to run a Pearson correlation test, you might also collect some other numerical variables, and maybe you want to check which numerical variables are related to which other ones. Basically, maybe you want to get an R value for every combination of two numerical variables. In that case, when you're measuring 3 or more, often a whole lot of numerical variables, and you want to statistically test for significant relationships among them, you're not doing a new test really, but instead you're going to write it down in a table that we call a correlation matrix. And what you do is just run a normal Pearson's correlation test on every pair of variables to get the R value for each of those pairs and see if each of those comparisons is statistically significant. So you'd have to check each one's p-value, see if it's below 0.05, and if so, you'd say, okay, that one's significant. So really, a correlation matrix is just doing this correlation test a bunch of times, but you'll do that if your design happens to have a bunch of numerical variables. If you want to do multiple correlations, you can lay it out in a table so it's nice and clear for everyone. Whew, okay, those are the most common and basic tests, although we will discuss a bit about some other setups like a factorial ANOVA to test for statistical significance in factorial designs and things like that. But for now, I just want to stick to these simple tests I mentioned, and in the following videos, I'll give a bit more info on each one.